Hello, everyone. In this section, we will extend these basic operations from one drone to multiple drones. Multi-drone systems can be used for applications such as cooperative inspection, search and rescue, environmental monitoring, and swarm navigation. In this notebook, we will first configure 3 drones in AirSim. We will then control them through one Python client, implement a simple swarm migration algorithm, and finally use multithreading to assign an important control task to each drone. Let us begin with the AirSim configuration file. In this example, the 3 drones are named UAV1, UAV2, and UAV3. Each vehicle uses the simple flight vehicle type. We can also configure its initial coordinates, as well as its initial yaw angle. After saving the configuration file, we restart the AirSim environment. We should then see all 3 drones at their configured starting positions. Now let us move to the Python code. We first import packages and the other required libraries. Next, we create a multi-rotor client object. One client can communicate with multiple vehicles. We don't need a different network port for every drone in their basic example. The program uses a loop to control all 3 vehicles. For each drone, we first call enable API control, then arm the motors and send takeoff commands. AirSim uses the NED coordinate system. In this coordinate system, positive X points north, positive Y points east, and the negative Z points downward. Therefore, Z coordinate of -3 represents a position 3 meters above the starting point. Now we define a helper function named getUAVPose. Each vehicle's local NED coordinates are measured relative to its own starting position. The notebook then defines several parameters for a simple swarm control algorithm. These codes means that the swarm should move toward a point 25 along the x direction. The algorithm combines 3 velocity components: migration, separation, and cohesion. For each drone, the separation, cohesion, and migration components are added together to create the final velocity command. The program then calls move by velocity z async. The first 2 arguments specify the designed x and y velocities. The z coordinate remains fixed at -3, so the drones maintain an altitude of approximately 3 meters. And this process runs for 500 iterations. A short delay is added between commands so that the simulator has time to process the control inputs. And I will run the code. The final part of the notebook demonstrates multi-threaded control. In the earlier example, one Python execution flow send commands to several drones. With multithreading, we can create a separate thread for each drone. The plan control function contains the complete task for one vehicle. The function defines 4 waypoints that form a square. The drone follows the complete path using move-on path async. Because these waypoints are expressed in the vehicle's local NED coordinate system, each drone follows the same square relative to its own starting point. All threads are started, allowing the 3 flight tasks to run concurrently. If we only reuse a single variable named T, it will contain only the most recently created thread. And now I will run all the cells.